Welcome to this NPTEL lecture on principles and techniques of modern radar systems. We were seeing the detection theory. The first thing that we saw was match filter. In the last class, we have seen that match filter output actually is something as a correlation function, and for moving target and for RF signals we have found that expression. So, today we will discuss the ambiguity in range and Doppler measurement. Now, to do that actually we will go back to equation 14 where we have said. So, equation 14, if you look back again, so that told us that SNR of the match filter at a time t is equal to T0, that was given by, for Gaussian white noise, 0 mean Gaussian white noise, it was given by 2Ex, but divided by the double sided power spectral density of noise. So, then the question naturally is that okay, so that means wave shape, that is not at all important for maximizing SNR, and if we keep the Ex at a fixed value and take any shape, that will do, that will give us the maximum SNR. So, but then that means the shape of the wave can be chosen by the radar designer. So, question is what is the best choice for transmitted waveform. So, since match filter is being used, so we can say that as long as the Ex is same, we can choose anything, but then the designers choose it at anything. So, one of the popular choice for wave shape, that means the transmitted wave x t. So, the question is what is the best choice. So, that actually is chosen according to the resolution concept. So, what is the concept of resolution? Resolution means that if we have two targets, suppose this target and this target, and this is suppose the radar. So, radar is getting echo from this as well as echo from this. Now, at the receiver, the radar will have to take a decision that whether there are two targets or one target. So, now suppose I go on decreasing this thing, decreasing the range or difference in range or the distance amongst them. So, how close the two targets can be, and still radar will be able to tell that okay, there are two distinct different targets, not same target. So, the minimum separation of the two target for which radar is able to distinguish them as two different targets is called the range resolution. So, similarly, Doppler resolution, what is the resolution in Doppler? That suppose this target has a Doppler frequency, its return echo creates a Doppler frequency FD1, and this target its Doppler frequency created is FD2. So, what is the minimum distance or minimum difference between FD1 and FD2, so that the radar will be able to say that okay, there are two different targets with velocity Doppler frequencies FD1 and FD2. So, similarly, this is the concept of resolution. As you see, you come across that when you go and buy an camera, you say resolution. Resolution in case of optical images, it is in terms of pixels. So, you say that I want in the linear or length direction I want 1024 dots, and in the width direction I want 760 dots. That means that between two dots, that means if you divide the whole page between 1024 dots, the length you divide between 1024 dots. So, suppose this dot. So, how many dots you can accommodate here? If you call 1024, that means if the length is L, you can say that L by 1023, this is your resolution. That means minimum separation between them that the camera will be able to detect as two separate dots. So, this is the concept of resolution. So, radar also, radar designers chooses this xt from this standpoint, and we will see that match filter again helps us to answer that what is the resolution, and also that whether there are two targets or one target. So, match filter is a beautiful thing, it maximizes SNR as per equation 14, but now we have last time we have come to equation 29, where we have seen that the output of the match filter that actually is some sort of correlation with some phase thing for a moving target. Now, we will further proceed. So, first we will discuss the concept of range resolution. Actually, Doppler is making two measurements, the velocity and range. Now, range measurement is direct, that means from the round trip time it measures range, and from the Doppler shift it measures velocity. So, first we will see the range resolution concept, because what I described that is a quantitative description, but finally we require some quantitative things, because we engineers always believe in some numerical values. So, we will have to say that what is the resolution of the radar sensor. So, for that we are proceeding. So, what we are doing first, let us say that let us consider first two echoes from, suppose I have a radar and let me give some different colors, that suppose this is target 1 and let us say this is target 2, the green one target 2, and let us say that both of them are stationary. So, they are not moving with time, but from the radar their ranges are, or suppose this distance is r1 and this distance is r2, okay, the two ranges, and since they are stationary, there is their Doppler shift is 0 for both of them. So, we can say that the delta r between them is r2 minus r1, and we are trying to find out what is the value of this delta r in terms of the radar's various parameters. So, particularly we are trying to choose an waveform which can give us the best thing. So, for to answer this question, we will have to again see that we are going back to our pulse radar and saying that the radar transmitted band pass. So, radar has, so I am saying transmitted signal, transmitted transmitted band pass pulse is, we know that it is a carrier modulated thing. So, we can express it as R t cos 2 pi f c t plus phi t. So, another one. So, let us call that this is our starting point today. We have seen up to equation 29. So, today we are seeing equation 30. So, what is R t? R t is the, if any amplitude modulation is there in the carrier, and phi t is the phase modulation in the carrier. So, correspondingly we have seen that we can write the pre-envelope, and the relation is that since this is RF signals, we will have to come to complex envelope. So, the intermediate root is the pre-envelope. So, we know that this is real part of the pre-envelope psi t. Now, so what is this pre-envelope psi t? That we know by now, that I can write it as R t e to the power j 2 pi f c t plus phi t. Okay. And that we know that now the complex envelope will come, that x t e to the power j 2 pi f c t. So, this, let me call this equation as 31. Okay. So, the what is the complex envelope value then? That I can write as the complex envelope x t is nothing but R t e to the power j phi t. So, this is our equation 32. Now, so this is the radar is transmitting, and again see that two closely separated targets, and in response to this x t, they are the received echoes, let me call them. Previously, I was calling x I t. Now, instead of calling x I 1, I am calling x 1 t and another near closely spaced target. So, x 2 t, the complex envelope of their received echoes. So, or let me say that this x 1 t, x 2 t is the received echoes. Okay, we will later put there a thing. So, then we can find their pre-envelopes. So, we can write that x 1 t, its pre-envelope I can call psi 1. So, real psi, or psi is the for transmitted signal. So, it is I can write t minus t 0. So, this thing, that means it is, let us say, delayed by a round trip delay t naught. Previously, we are calling it x I t, now I am calling x 1 t, that is the only difference. So, and I can write x 2 t that is L pi by t minus t 0 minus let us say tau. So, what is tau? Tau is the difference in delay between the two stationary targets echo, as simple as that. Now, suppose we make that time reference for my whole case is at t is equal to t naught, and without any loss of generality, I may say that let us make t naught is equal to 0, otherwise every time I will have to go on writing t naught. So, now the question is that these two echoes, you see that the question is these two echo, from that the radar will have to say that there are two different targets. So, the question is two targets, what is the smallest value of this difference between their range delta r, so that they will be said by the radar that they are two distinct echoes. Now, so to answer that, let us again find the square error. So, actually we have seen that the two echoes has pre-envelope like this. Actually, the radar will process those complex envelopes. So, let us form the error, square error, because x 1 or x 2 any one may be at greater range. So, we are making square error. So, that is that minus infinity to infinity psi t minus psi of t minus tau. You see tau naught I have made 0 without loss of generality. So, this. So, let me see this error. Now, obviously, if this error is very small, then I will say that no, this is the same target's return, and if it has a substantial value, then we will say that these are two different things. This is obvious from our common sense, we can say. So, now let us manipulate this square error. Actually, this is one of the measure people found that okay, in the pre-envelopes their difference, the magnitude part of that difference, and then let us square that, because which one is larger that we do not know. So, let us square them and integrate that for all time, and then say that okay, if that error is substantial or below a threshold, you can say okay, they are same, coming from the same target, and obviously, if they are from different targets, then the error will be substantial. So, that is okay. So, let us now manipulate this, that minus infinity to infinity. So, this is the complex number. So, magnitude square. So, we know that this we can write as psi t minus psi t minus tau, then the complex conjugate. So, psi t minus psi t minus tau star dt. And if we go further, So, I can open up now, and I think you will agree that I can write it as okay. And if I see again these psi t things, I think you will agree that magnitude of this square, that means A. So, that can be related to the x t, or where is our x t? So, psi t is equal to x t to the power j t power 3. So, psi t, its magnitude square, can I say that it is equal to x tilde t, that means complex envelope magnitude square, because this term e to the power term, that will have a magnitude of 1. So, I can write this to be same as x t square dt plus that also will come same. So, I can write 2 of these and then this thing as it is minus this also you can say a b star plus a star b, we know that is 2 of real part. So, for complex number, so I can write minus 2 real, then or I have put x here. So, basically this t minus tau dt. Okay. So, this bracket should be closed, and if I change to from psi to the our this is complex envelope I will have to write. So, 2 we know the relation between pre-envelope and complex envelope. So, I can write it in terms of complex envelope, that it will be actually, if you do, there will be a phase term coming, just simple mathematics. So, e to the power minus j 2 pi f c tau, then the integral will come. You can simply do this, because we have the expression, you put it, you can get that x star t x t minus tau dt. Okay. So, this is our next equation, that will be equation 36. Okay. Now, the question is, so what is this side? Let me write it, that our that squared error. So, this is equation 36. Now, you see this x t square, that means whatever is my transmitted signal waveform, it is nothing but the energy of that, because complex envelope will be the energy of the complex envelope will be the same as the actual transmitted signal. So, this part is constant, for a given waveform this is constant. So, this square error that will be minimum when this integral part, this second term in the RHS, that is maximum. So, also that needs to be positive. So, I can say that this this is minimum when this is maximum and positive. So, this is the requirement that now what is the second term? It is a varying function of tau. You see, actually I should write it. This thing is dt and this is this. So, this is an integration of in running variable is t. So, actually this thing will be tau, and then there is a phase modulation tied to carrier frequency. You see, both these are functions of tau. Tau is the delay between the two echoes from the two times. Now, so this integral, let us define that this integral. So, let me give it a symbol, some zeta r, because it is concerned with the ranges. So, that x r tau, it is a function of tau. What is this? This is that integral portion x star t x t minus tau dt. This is our equation 37, and this equation is called this function is called range ambiguity function. Actually, it should not be said ambiguity function, it is a misnomer. Actually, it is opposite of ambiguity, it helps to resolve ambiguity. What is ambiguity? That thing I was saying, that if this goes very high, that means actually you can see this. What is this? The right hand side is basically correlation of the transmitted signal with its some delayed version. So, if that is high, then we will say that is from the same target. That means, the peak in this ambiguity function, that tells us that there is only one target, whereas if I get a very small value of this correlation, I say there are two distinct values. So, it helps to do that, that is why it is range ambiguity function. Later we will understand it more, but now the name is. Now, you can please compare this with compare 37 with our that output of match filter for stationary target, because this is for stationary target we have seen with 26. 26 was the match filter output for stationary target, and you can see that compare this, you can see if I put in that equation 26 T 0, which was the total delay, that to 0, then output of match filter for a stationary target at 0 range is similar to this, is similar to the range ambiguity function. So, you will see that they have the same envelope, but different phase. This indicates that match filter not only provides maximum SNR at output, also is preserves the range resolution characteristic, because I can resolve range by this, I can separate two targets by this, etc. And also I can say that this XRT, it is nothing but a, I can say, autocorrelation function of X, complex envelope of X. So, obviously, for tau is equal to 0, it will have maximum. So, I can say this, that the ambiguity function is maximum at this, we know from our undergraduate knowledge that autocorrelation function for 0 delay, that will be maximum. So, when this will come, I will say only one target is there, that means these two targets they are same. So, even if they come from different, I will, my inference will be that they are from the same target, because autocorrelation is high. But also you see, now we can answer that question, that what will be the shape of x t. If this autocorrelation function have a sharp drop, then the slightly away from that, if there is a target, the autocorrelation will be very low. Autocorrelation at that time, it will be called cross correlation, will be very low, and I will be saying no, there are two targets. So, ideal, I can now say that ideal this range ambiguity function is a delta function. That means, it will be have a peak if I plot it at versus tau versus this x at tau magnitude. Actually, generally in ambiguity function only the magnitude part is plotted, because phase part is complicated and we do not do that. So, if I get a delta function type of thing, that at tau is equal to 0 I have a peak and then thereafter another, then every range will be resolvable, because just away from that I know that it the autocorrelation will give 0. So, I will be saying no, there is another target. But obviously, in life you cannot have this type of autocorrelation function. So, we require that it should fall very quickly from 0. So, that means actually the in real life you do not have that, but what we want, whatever shape, I am not saying that, but the closer it comes to 0, that is better. That means, suppose I have one such shape and another shape is this. So, obviously, this green one I will prefer, because here the autocorrelation function is coming closer here and resolution is higher for this, because the width is less. Actually, this width is the main thing. That means, in till this time, that this width, that means from 0 to coming again to the next null, this width is now the resolution of tau. So, if we put it back into our range resolution equation, then we will get that. So, most desirable shape, I can say that practically. So, what we have discussed is desirable x at tau is that sharp peak at tau is equal to 0 and high roll off around tau is equal to 0 and then the null or first null width as low as possible. Now, here drawing I have drawn this shape, it can be anything, it could have been triangular, it could have been rectangular, anything, but the most important thing is within this zone. So, when I am at this green one, you see that anything separated by this, anything which has a separation of this, any two targets whose separation between them is within this, I will be always saying no, 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 it is from the same target. So, the width, null width is the main thing. So, as from the peak, that means 0 range, that means 0 separation, to the this width of the first null, up to that I will say that it is from the one target. So, I can easily now say that what is, now I can answer that final question, that what is my range resolution? We have said that minimum separation between the two targets, that is C delta tau by 2, where what is this delta tau? This is the, this is important understanding this, delta tau is the width of the first null of the range ambiguity function, exert tau function. So, if we can easily find out this correlation function, if I have a given shape of the signal, then I can find out that first null and I immediately get the range resolution. I should give it a number, this equation. So, this equation is, I think it is our equation 37. So, you see that from the match filter output, we have got the range resolution equation, we have quantified, as we said at the start of the lecture, we can quantify, and the range resolution is nothing but C delta tau by 2, where that is the delta tau is the first null width of the thing. Now, null is a choice, generally we choose null, but you can have that from the peak, you can have 3 dB, 6 dB, whatever, what is practical, what for that application. So, under something that width will now matter, if it is 3 dB maybe at this point. So, this will be then the thing, but so I will not say null is always width of the first null or width of a threshold level, width at a threshold level, that will give us the resolution. So, I end it here. Next day we will see the Doppler resolution concept similar to here, and from there we will come to the concept of ambiguity function in general, because it should be a two dimensional thing. I have both these measurement to make. So, we will come out with a two dimensional ambiguity function. Thank you.